soon. I think it's recording now. So thank you so much, and apologies for the late start. It was just I had a bit of a clash with my this Friday with my normal schedule at work. So, and also I wanted to do some of the diagrams instead of writing stuff that could make it a little bit the slides a little bit too wordy. So I decided just to make some diagrams, and they were a bit of a time consuming to do that. So yeah, that's why we are starting late. Finger crossed there are no typos. If there are typos, errors and these things, that's a good. It could be a good thing, especially on the technical side. So yeah, let me go. The slides are okay, right, George? Just before I proceed.
Slides are good.
Good. Yeah, so this is the agenda for today. We'll just go through the usual stuff quick, very, very, very briefly. And then the main session, we will revise just a quick recap on discrete logs over cyclic groups. Remember last time we defined them over cyclic groups. We could also have defined them over abstract groups, but then the discrete log is not then guaranteed to exist. That's why we decided to do it in over cyclic groups, because it always exists. Finding it is another question. This is why cryptographers love cyclic groups so much, because they can build cryptographic systems, discrete logarithm type of crypto systems over cyclic groups. And then we'll recap also again on the discrete log problem. We will go through the Diffie-Hellman problem. This is a bit trickier. Yeah, so George, you are saying there's a usability thing with the chat.
Yeah, this was a suggestion for Crowdcast if they're monitoring.
Yeah, I think some of them after the lectures, after the session ends, they because we are one of the beta users, they will come in and check the chat for any feedback. So by no means, please feel free to leave any feedback you want for them. They will see the chat. Yeah. So going back to the agenda, so we will review the Diffie discrete log problem, but then this one is a bit trickier, because normally the Diffie-Hellman problem is is introduced after you introduce the protocol. But in my case, I will do it abstractly in order to see, in order to help you see the relationship, whether there is a relationship between the discrete log problem and the Diffie-Hellman problem. Okay, I think it's easier, it's cleaner that way than introducing you the Diffie-Hellman key exchange protocol and then stating the problem in a concrete. But by doing it abstractly, it helps you try to connect the dots between the discrete log problem and the Diffie-Hellman problem. Okay, you'll see what I mean. I hope, anyway. I hope it doesn't backfire. It won't confuse you. Okay. Yeah, and then we will briefly define the notion of symmetric cipher, symmetric crypto system. And then we will ask the question, because symmetric crypto system means that, you use the same key, two parties, in this case, our friend Amir and Bob communicating, they need to share the same key. Yeah, so the question is how? And we will assume that, our friend Amir and Bob are living very far from each other. It's unfeasible for them to be traveling and deciding on the key all the time. So they want to do it electronically, and we'll assume that the channel by which they are doing they are communicating is unsecure. You will see what I mean anyway. Yeah, so that's where we are. Okay. That's what we'll cover today. Okay, it won't be. This is not a lecture on cryptography, because obviously there's a lot to cover when the time in the topic. But this is just to give you a flavor, of how simple mathematical notions that you learned in this crash course. In this case, the notion of a cyclic group, and even the notion of the basic notion before that, even of exponentiation in the group sense, can be used to build very powerful cryptographic systems. So this is also part of a new philosophy that part of the feedback I got from the past 2 crash courses was that the crash courses were too abstract. So this is my answer, to try to get the abstraction and then try to see how the abstraction is applied in real, in interesting use cases. So we will do today cryptography. And then I think Bob will do another talk on something else after we introduce the notions of orbit and what other notions that he needed. I'm not sure. But yeah, we will have another applied topic also on group. Yeah, but this will be the last session of, we will talk about cyclic groups. Okay, so this is where we are. In the grand scheme of things, we're still in groups, in this case, in abstract sense. Obviously, we've been focusing in the last 3 sessions on cyclic groups. And then eventually, we want to move as fast as possible to matrix groups, because these are the prototypes of our main goal for this course. I forgot to mention that, which is the course that we'll have in the summer on Lie groups and the representation theory. So, and after that course, we will have a applied mini school on quantum error correction. So you can see how Lie groups and a few other stuff that you will learn can be applied to stuff like quantum error correction. And hopefully we'll have also on quantum machine learning. Now, this is quantumformalism.com. Our company, we are planning some other courses that we will probably do them in parallel, which you are happy, we are, we are more than welcome to attend. We will have one course on category theory, applied category theory for computer scientists, for instance. We'll have that. We will probably have another course on dedicated cryptography as well at some point. So yeah. Okay. So enough of blah, blah, blah. Let's get started. Can you see the slide properly before I go through this? Yes, okay. It's very thing that when it seems when can you see the pointer? It seems when I upload the slides on, this is one of the bugs that I need to give them the feedback. You don't see the pointer, so you cannot see me move around the pointer, right? On the slide. Yeah, because that would be handier. Yeah. If it's okay for you guys, I could try Google Slide as well, if it makes you better with the pointers or without pointers, so it doesn't matter. Would the pointer help as I talk through, or you will be, it's okay,
It's okay for me.
Okay, anyone else? We could try. I think it works with Google Slides. It's just someone. Okay, no pointer either way. Okay. Yeah. Okay. Yeah.
Whatever is smoother for you.
Yeah. For me, it doesn't really matter. But I'm using the pointer for myself anyway, so I'll be pointing just to help me think where I'm talking. Yeah. So. Yeah, so let's revise the notion of a discrete logarithm over cyclic groups. As I was saying, this notion of a discrete logarithm can be defined on an abstract group, but then it's not guaranteed. The discrete logarithm, there might be some elements of the group where it doesn't exist, right? So that makes life a little bit harder for us, right? So for that reason, it's much more easier certainly for our purpose to just define the discrete logarithm in a much more narrow just on cyclic groups. So given a group G generated by this element, by now you know what a generator is, okay, and the group has order n, then by definition of a cyclic group, okay, for each x in the group, for each group element, there must exist an integer, right? Between 0, I mean 0 is trivial. Yeah, okay, yeah. I mean we can leave it there. Between so there must exist some k between 0 and n minus 1 such that this thing is satisfied. So the generator to the power of k will yield the element x. Okay, this is for any element of the group, right? Because this is the definition of a cyclic group. Okay, so this integer k is called the discrete logarithm of x in respect to the base or generator g. Okay, and the notation wise, we write log g of x, right, to denote this. Okay, to denote the fact that k is the discrete logarithm of x in respect to base g. Okay, or generator. Okay, just as a side note, those of you who haven't attended the previous session, there's another name for this generator. We are using the group theoretic jargon here, generator. But if you are coming from number theory, they use primitive root. Okay, and very often cryptographers use the term primitive root as opposed to generator. But because we are in group theory, we are using group theoretic language, and for that reason, we are using the term generator. Okay, so it means the same thing. Primitive root and the thing and generator is the same thing. Okay, so here's a toy example. I think we went through this toy. Did anyone find any typo? I hope not. So here's a toy example. We have the multiplicative group F5 star, right, made of 1, 2, 3, 4 under mod 5 multiplication. So 2, I claim, is a generator for F5 star. Okay, and then the discrete logarithm of 1 in base 2 equals 4, right? Because the claim is that 2 to the 4 is equals to 1. Okay, the same with this other example, and so on. Okay, I hope I didn't make any typos. This is the danger of the thing when it comes to concrete stuff. Okay, so we are all on the same page. Let me check the chat. So far, so good. You know what a discrete logarithm is, giving a group, giving a generator. I mean, giving a cyclic group, right? So no problem. We are all on the same page, right? No one has any problems with this. Good. And now the actual problem itself. Okay. So now, given a cyclic group G generated by this element, obviously we are talking in abstract. At some point we will in the concrete example, and later we'll see which type of cyclic groups are in practice being implemented in cryptography. So giving a cyclic group, for now we can state this abstractly for any cyclic group, right? Giving a cyclic group G with a generator small g of order n, right? It's always very important to state, to understand which order you are working on, because this is where the complexity of computing it is. The larger the order, the harder it becomes to do this. Okay, so let's assume order n. Okay, and let's suppose x is a group element. So the discrete logarithm problem is exactly that, as you might I forgot the word I wanted to say. As you can guess, is about computing the discrete log in base g of x. Okay, so in other words, find the integer k between 0 and n minus 1 that satisfies this. Okay, now we have seen before, I was mentioning, for some groups this is very easy. For the additive group, for example, this is equivalent to this equation here. This is like I won't say kindergarten stuff. This is like very very easy to solve. But for certain groups, like when you write the group multiplicatively, say for example for the multiplicative group f p star, computing this is equivalent to solving this. I think your gut feeling already tells you, your intuition. This is solving this equation here is far more. This problem here is far harder than this one, right? And here's a toy example of this. So this is a more of a challenge. So in this case, let's consider f 11 star, right? Where 11 obviously is a prime number. So the claim is that 2 is also a generator. You can verify this later. Now the question is, what is the discrete log of 9 in base 2? In this case, in this multiplicative group F11 star. Let's see if some people can guess. Is it 3? Who thinks it's 3? I hope I didn't make. There is at least one there. I can guarantee you that. If I didn't make any mistake, if I did, that's a great thing actually. If you can point it out to me, I was doing this fast, so yeah. It's. I can tell you that it's not 3 because 2. Because 2 to the 3 is not equals. It's not this. Do you agree? It's not 3. What about 4? Okay. It's okay. I'll leave this as a challenge for you, but there is at least at least one. Okay. So it's not 3 actually. So I can tell you that. So that leaves 3 other options. The question is which one? Yeah, you will figure it out. You know, it's just with the pen and pencil. You know, it's very hard. It's not a thing to do it with in your head. So I won't hold you to that. Don't worry with it. And then in case you don't find any that satisfies this, then it means that I made a mistake. But I can assure you that there's at least one there. Well, it must exist anyway. So, right? Because you know, F11 star is a cyclic group. We agree with that. Okay. So far, another question I want to ask is: no one has any problems with the thing about this cyclic group. I mean, the statement of the discrete logarithm problem. Everyone knows what the problem is asking, right? Is that just your comment, George? Is that that's the case for you as well, right?
Yes.
Okay.
I'm having a hard time reading the slides and following.
Okay, no problem. I can actually, if it helps, I can give you the link to the Google slide if you want.
Yes, but it's okay. We can work on this also in the review session.
In the study session, yeah. So that's fine. So let me go to the chat. Nobody so far. Everyone. I hope I'm still, because I cannot see the chat. Yes. Yeah. So. Yeah. So everyone understand at least what the discrete logarithm problem is trying to solve. I actually find it, you know, stating it in this group theoretic sense is actually much more easier to understand than, you know, the usual way that computer scientists introduce the same problem. At least from my point of view.
Yeah, I agree. For me, it strips out some inessential things.
Yeah. Okay. So now, this is the trickiest part. So this is the discrete logarithm problem. So I want to go now through another problem, called the Diffie-Hellman problem. Okay. Normally, as I said at the beginning, this problem, the Diffie-Hellman problem, is normally stated after introducing the Diffie-Hellman key exchange protocol. But I'm trying to do it here, hopefully, because it helps you by being this abstract, you know, try to, you know, find the link, a relationship between the two. Okay, that's why I'm doing it. I hope it doesn't backfire. Okay, so the Diffie-Hellman. Actually, before that, I wanted to make some comments about the discrete log problem. As you can see, I'm not even sure about the sequencing of my slides because, you know, this tells you how rushed I was in doing them. So just a comment before we state the Diffie-Hellman problem. some comments about the discrete log problem. So there is no non-efficient classical algorithm that solves the problem for cyclic groups of say large orders. For example, there are some algorithms that do it, like what's this thing? I never know how to call it. Baby step, giant step algorithm. And there are a few others algorithms that do that, but at some point, as the order gets larger, it becomes impractical. Okay, this is what makes DLP a good security assurance, if you will, to build classical cryptographic system. Here I'm using classical in the sense of being non-quantum. Okay, this is what gave birth to the something called discrete logarithm cryptography. Okay, these are like cryptographic systems based on the discrete log problem. Some of them are this, the Diffie-Hellman key exchange protocol that we will touch today. The other very interesting one, the Elgamal encryption. Even though we are not touching it, this should be a piece of cake for you guys to understand Elgamal encryption. Really, at least have an overview how it works. So this is the beauty of this. Once you know cyclic groups, the thing it's the simplest way for you to get into, I would say, into because group is a far more simpler structure than say rings or fields, this type of stuff. So by going through cyclic groups, it essentially opens the door for you for other cryptographic systems like Elgamal encryption, digital signature algorithm, even elliptic curves cryptography, hyperelliptic curves cryptography, all these fancier stuff. The door is open for you. A final comment I want to make on this is that, especially for those of you, because this is quantumformalism.com, there is a quantum algorithm, Shor's algorithm, that solves DLP. So in a sense, this means that when we have useful quantum computers at some point in the future, all the protocols that depends on DLP will be obsolete. Okay, so you can read the Shor's algorithm. I think his seminal paper is called Algorithms for Quantum Computation, something like that. And then he goes on to say discrete logarithms and factoring, something like that. If you Google it, you will see it. Yeah. We won't go into that because we don't have the language, the quantum computation language, for us to discuss this. But hopefully at some point we will come to this in the future when we talk about quantum cryptography stuff. At some point, I'm sure we will have opportunity to do that. Okay. And on a side note, this again, we don't have the machinery, the technical thing baseline to discuss this. Is that this the quantum algorithm actually Shor's algorithm for DLP is actually related to something else called the hidden subgroup problem. Okay, this is just for the super curious. You can go and research this. This is just side note. It's not something that we should worry about here. It's out of scope. Okay, so now I'm going to, hopefully it doesn't backfire, the Diffie-Hellman problem, and I hope I didn't make any typo, in abstract sense. Okay, so given a cyclic group G, okay, generated by the small g of order n, okay, of order n, okay, and an element of the group X, okay. Actually, I think this there's a typo here, but it doesn't matter. Given, okay, so I think we only need. I'm actually confused with my slide as well. Yeah. So let's just say we need the generator. We have the order, and we have two secret integers. Okay, integers that we don't say we don't give to anybody. Okay, these are like K1 and K2, also in the range of 0, between 0 and n-1. Okay, and assume that G, the generator to the power of K1 is given, and the generator to the power of K2 is also given to you. Okay, so the problem is to whether you can determine this G when No, actually, this is not given to you. This is given to so these two, when they are given to you, whether you can determine g to the power of k1 times k2. Okay, this is one of the problems. Try to state it abstractly without stating the protocol. I guess this is one of the thing, but I guess it's clear. I hope it's not confused. Ignore this. So you have two secret integers, k1, k2, okay? And you are given these guys, these two guys. The question is, can you determine this? And here's something, some piece of information that I'll give you is that this G, the generator to the power of k1 times k2 is equals to this, okay? This is just a property of exponentiation. This is where you need to go back to the, when we were defining the group exponentiation stuff, especially when I defined it much more cleaner. Which lecture was that? I forgot. So you need to remember the properties, okay? So the question is whether solving DLP means solving DHP. Say for example, there's an algorithm for solving DLP. Does that follow immediately that we can solve this? What's your feeling? First of all, is this someone is asking, will you be dropping the link of the slide? Yes. Yeah. Yes, I will be dropping the slides. Yes, I was just seeing some chat. Yeah. So first of all, no one is confused with this, right? This thing. This is danger. My thing of backfiring is giving this problem in abstract without without giving you the protocol. This is the thing. You will hopefully the point is that after we go through the protocol in the next few minutes, you will see why this is related to the protocol. Why solving this problem means breaking the security of the protocol of the scheme. Okay. So this is not confusing. Sorry, I was rumbling around because myself I was confused with the thing. There's clearly a typo. This is, I don't need to put this X here. So it's just giving a cyclic group with the generator, given two secret integers, k1, k2. If you are given the generator to the power of k1 and the generator to the power of k2, whether you can, based on this information, having these two guys, whether you can determine this, okay? And also, again, as I was saying, recall from the group exponentiation properties in few sessions back, this thing equals to this, okay? We'll come back to this. And now the question is, if you solve the DLP problem, which means cracking the discrete log, means solving the this problem, Diffie-Hellman problem. So I saw someone saying yes.
Yeah, I think I see it in the direction, Dimitri, that DLP implies Diffie-Hellman, but I'm also not sure the other way around.
Okay. That's keep this in the thing. This is very, very, very interesting. Yeah. So the other way around. What about the other way around? First of all, is there anyone who doubts, who thinks DLP does not imply DHP? So that means we are all in. Everyone is in agreement. Yeah. So Beren say yes, but I would just say guess. Yeah. So yeah. So is there anyone who needs a second thought? Yeah, I won't confirm nor deny, but I will say you are in the right direction. You take it to the study session to see if you have a final thing. Yeah. Now, this is actually, I'm already like very happy for you to already conclude this, because this tells me that it's actually good that I defined the problem in abstract before giving you the protocol. Yeah, I think it's much more cleaner. This is one of the reasons I did it, was to do it so you can see the in abstract without bringing the protocol itself, because this is a mathematical problem, right? So, you know, before the actual underpinning protocol where this matters, so you can see that I tend to agree with you, I would say, yeah. Now, what about the other way around? That's where it's not clear, because if that were the case, it would mean that the two problems are equivalent. Solving one is equivalent to the other. But you know, as far as I know, no one has been able to prove that. Okay. Another question is whether DLP is the only way to solve the discrete, the Diffie-Hellman problem. Remember, the Diffie-Hellman problem is about determining this guy, right? So the question is DLP the only way to crack DHP? What's your gut feeling? Maybe when we define the protocol itself and you know, discuss some of the attacks, like for example, man in the middle attack, for instance, you know, that might help you give a hint.
My gut feeling is that if both of the previous implications are true, then the answer is yes. But if Diffie-Hellman doesn't imply discrete logarithm, there might be another way.
Okay.
That's just my gut.
Okay. Anyone wants to throw in? Right. Remember, the Diffie-Hellman problem is about determining this, knowing these two guys, whether you can somehow determine this. The way you do it, it doesn't matter. You know, you could use social engineering or something in practice. Can you trick two parties, Amir and Bob, to? Okay, it seems like maybe I'll leave this to you guys to think about it and maybe discuss it on the study session to see whether this is the case. Okay, so that's the Diffie-Hellman problem. Now let's go to the notion of symmetric ciphers. Okay, so symmetric ciphers means ciphers, cryptographic systems where, you know, two parties, you know, in this case, we will use our friend Amir and Bob. They want to communicate. They need to have the same key. The problem is if they are, you know, separate, how can we make it convenient for them to, you know, to mathematically generate the same key, you know, without having to be, you know, in contact with each other, you know, and assuming that they have, you know, they have to communicate whatever details they have to communicate in order to either of them to generate the same key is unsecure, is being monitored by Eve. So at this point, I'll stop sharing because I have the other slides, the other thing, because I put the stuff on as diagrams. Let's see. How do I even stop sharing? Was I sharing, George?
Oh yes, you were sharing.
Yeah. Okay, so
there should be a stop sharing button.
Yeah, there's something here. Okay, so you must have stopped seeing the slides, right?
Yes.
And now, finger crossed, we will go to the, let's see, this is where it gets trickier. Screen. Let's see if I can see a window. Can you see this window? Can you see this?
Yes.
Okay, can you see the diagram? Maybe I can maximize it. Let's see.
It looks, I just see a couple of icons. It's hard to see.
Okay, is everyone else on the chat in the same thing?
It looks like a menu of icons.
Is it? Okay, maybe is it the same for everybody?
Yes, others are also just seeing folders.
Okay, so maybe I have to do this. Let's see. I will share slide. Let me upload a file. I have to share one by one. It's a bit inconvenient, but it's the only way, because the how do you say, the diagrams, they wouldn't fit properly on the thing. It wasn't clear enough. I didn't like it. Let's see. Upload and convert. Finger crossed. I haven't tried to even do bulk. Okay, can you see?
I see a diagram now.
Is it clear enough, this diagram? Can everyone see? I don't seem to be able to maximize it, but is it clear enough? Can you see the test?
Yeah, if I maximize the shared screen, I see it okay.
Okay, what about the rest? Is Barry saying, okay, clear, but too small? Let's see if I can do something. In fact, let me try something else. Let me see. Another way of sharing.
I think it depends on how big a screen people have.
Yeah, maybe I will do share all screen. Let's see. So you should see yourself. What about now? Can you see the slide? I mean, a diagram. Is it better now?
That's better.
Okay. What about for everyone else? Let me see if I can even make it better, even bigger. Sorry. How do I exit this? Yeah. Okay, let's see. Is it cleaner for everybody? I cannot see the chat, by the way.
The majority in the chat says it's okay.
Okay, but what about yourself? You can see clearly, right? I can share these. I'll upload these diagrams also later, so you can see this.
No, I have the same issue that I can't see it clearly and follow the chat. I need to get a big screen, then I can have, or external screen, then I can have multiple windows.
Okay, but the rest can see. Everyone else can see the test and can see the thing. If they feel comfortable, so I can just walk through this quickly.
Yeah, some people are able to zoom in on the.
Okay, good. Is it clear? Yeah. And the pointer, is the pointer working, by the way?
I think I see the pointer here.
Okay. So let's see now. Okay. So we have two parties, Amir and our friend Amir on the audience, and Bob. So they want to exchange a message. So Amir has a message M that he wants to send to Bob. Okay. At this point, I want, everyone knows, all of you are coming from technical background, you know what cryptography is. So I want think so we can dive straight into it. Okay. So Amir has a message that he wants to encrypt, a message that belongs to a set that we call M, the set of all possible messages, okay, the message space. To encrypt it, to send it, before he sends it, he needs to encrypt the message, okay? So he applies a function, encryption function, that takes this M and takes a key to produce a cipher test, okay? So E is a map, and more formally, the encryption is a map between, the Cartesian product of the set of messages and the set of all keys, in this case, the key space, to the set of ciphertext. Okay, the ciphertext is the messages that nobody can read. It's like nonsense. Okay, so the key belongs to this set. Okay, so E is a function that takes as argument M and K to produce a ciphertext. Okay, so when Amir does that, he then sends the ciphertext through an insecure channel. Okay, being monitored by Eve. Okay, this is insecure. Do you say unsecure or insecure?
Dimitri is asking if it's possible for others to join with voice. That would be easier to communicate.
Okay, yeah, I think they can join because the stage is open. Let me just check if I put open stage. Yeah, I think everyone can join. It's open stage. I'm not sure whether Crowdcast
if you
makes it.
see a plus next to your own icon, that is a plus to join the stage.
Yeah, but everyone can see. Let me go back again. I'm maximizing this to the thing as far as I can in order. Let me go back like this. Is it bigger now? Is it better now? Can you see much more?
Better. That's better.
Okay, good. So I cannot see when I'm on this mode. I cannot see the thing. So okay. Anyway, going back. Thank you, Barry. By the way, it's insecure. Thank you. Yeah. So Amir encrypts the message. Okay, using obviously the message M using a key, right? A key that a private key that only he knows. It turns out also because Bob also needs to know this because this is the purpose of a symmetric cipher. Okay, and then he sends a ciphertext over an unsecure channel. Obviously, Eve is listening to it. Okay, here we are assuming that Eve can only have access to things there. She cannot manipulate anything here. Okay, so that's the key, because if she can manipulate, maybe she can change the stuff and send it. You'll see this. This is one of the ways of mounting a man-in-the-middle attack to Diffie-Hellman, for instance. Okay, so we'll see she's just listening. See anything that goes through, she can capture and store and try to make sense of it. Okay, and she gets the ciphertext. This makes no sense. It goes through. Bob gets the ciphertext. Bob uses the decryption function, okay, D, which takes as an argument the ciphertext and the key, the same key that Amir used to encrypt the message, okay? And then the magic is that Bob will be able to recover the original message that Amir wanted to send, and vice versa. Bob can also do the other way around, can send a message. Okay, so formally the decryption is obviously a map between on the Cartesian product of the ciphertext space and the key space. Okay, and it takes you to the message space. Okay, now in practice, a good practice in cryptography is that the algorithms, both E and D are, everyone knows about this. Okay, even the thing, there's something called Kirchoff's principle. The only thing you keep secret is the key. Okay, a good cryptographic principle is that everything else, everyone knows, except the key. Okay, so, and in practice, normally these guys are, algebraic structures. In our case, we are mostly concerned today about K. In this case, this big K, this set will be a multiplicative cyclic group. Okay, so far so good. So everyone now what symmetric cipher is, right? It's a scheme of communicating between two parties. In this case, we call them our friends Amir and Bob. Where they have the same key to do the encryption and decryption of the messages, of the communication that they want to exchange. Now, the question that we ask is, how do Amir and Bob get to agree which key to pick? There's like zillions of them, right? This set could be in practice. This obviously in the thing is finite, but it can have thousands, if not millions of elements, right? So how do they get to decide which key to use? And even more, how do they do that without having to, be in physical contact with each other, for instance, over electronically, where they can share some piece of information, and somehow in a magic happens, somehow they can, both with the piece of information that they share with each other, they can reconstruct a key that's equal, the same key, essentially. So how do they do that? Okay, so this is the essence of the Diffie-Hellman key exchange protocol, which is a beautiful protocol, as you will see, and it uses, very genuine fact of cyclic groups, So that's what we'll go next. Let me go back to the chat just to see if there's anything pending. By the way, am I still on, George? Because I've been talking and I'm not sure if Dimitri also joined. I can see him on stage.
You're on. I can hear you.
Oh, okay, good. Thank you. So everyone can see the slide, okay? So let's go. Let's see the protocol itself. Let me let's see. I hope I didn't make typo. That's why it is it big enough, or you want me to maximize it or minimize?
Looks good to me.
Okay, so everyone can see. So this is where I hope I didn't make typo. This is why I took time to do the slides, to do the diagram, because I think explaining it this way it's probably easier than writing it, the steps in words. Okay, so again we have the same thing. We have Amir and Bob. Okay, now the problem here, they want to exchange, they want to be able to generate the same key so they can use whatever the symmetric cipher that they want to use, whether IAS or any other that they want to use. Okay, so the first thing they have to do is to agree on the cyclic group. Okay, so they say, publicly, this is also known to everybody. Anyone who wants to communicate with them knows this. Even Eve herself knows this. Okay, so a cyclic group G of order n, and most importantly, a generator. Okay, this is the key. They need to pick a generator. Which generator? So this is the essence. So they agree this. Everyone knows this. So the way, so we will, in this case, I will walk you through this. We will go this way. It's easier to understand each step. So just follow the arrows in order to understand this. I will share these diagrams later so you can try to make sense of it and even potentially correct any typos. There is already one typo I can see here. So this meant to be n-2. So anyway, so the first step is Amir. Let's say Amir wants to communicate. So Amir needs to send the key piece of information for Bob to be able to generate the key. Okay, so let's say Amir initiates the key session. Okay, so Amir picks a random number. Let's call it KA, A standing subscript A standing for Amir, between 1 and n-2. Okay, there's a technical reason for this that we won't go through it, but this is in practice what cryptographers do. You can search this independently. So ignore that for the fact for y n-2. It doesn't matter for now. But let's say this is a good practice. Okay, so Amir picks a k between 1 and n-2. And then computes, something, an element that we call A, which is given by raising, by taking the power of the generator. That's why it's important to agree the generator, right? To the power of Ka. So this Ka that Amir just chose randomly. Okay, let's not even discuss what randomness means and all this. Ignore that. Let's say Amir has an option. N is very large. Amir just goes and picks some Ka. Okay, and then takes that Ka and then apply the power of Ka to the generator. And then Amir sends A. Okay, Bob receives A, and then the next thing that Bob will do is for himself to pick a random K, okay, that we call KB. Okay, so between 1 and n minus 2. It's not n minus 1. Okay, it could also be n minus 1, by the way. We just in cryptography, in this case, in the Diffie-Hellman, people use this n minus 2. This is a good thing. There are some technical stuff that we don't need to go through it. Let's just focus on understanding this first. Okay, so Bob receives the A from Amir, which resulted in, as a result of Amir applying, G, the generator, to the power of Ka. Bob receives that, okay? And then what Bob will do, Bob will take the A and do another power, take the power of raise it to the power of KB, the key that he just chose randomly, okay? And this will be the secret, Bob's secret key. So I call it SB, okay? Now, Bob has a secret key, SB, okay? Thanks to Amir. Now, what Bob needs to do is to help Amir get a secret key as well. So what Bob will do next is to generate out of the private key that he chose randomly, KB, he will do the similar thing that Amir did, which is to take the generator and raise the power to take it to the power of KB. And then the result of that, we call it B. Bob sends B to Amir. And then Amir will receive B, and then all he has to do is a similar thing as what Bob did here, which is to take B and raise it to the power of his secret key Ka, and then voila, we have the two. So the theory, the claim is that SB, SA, which is Amir's secret key, is the same as SP, Bob's secret key. The reason for that is because of the group exponentiation property, right? Because SA is equals to this, and this is essentially this. Let me maximize it for you to see how beautiful this is. Let me just, this, can you see? There you go. So the secret key of Amir is, which resulted in B, remember B is this, right? B is equals G to the KB, and this is equals this, and this is this, right? The property of group exponentiation, okay? Similarly, SB, the secret power of B, of Bob, is A, which Amir sent him, is equals to this, and this is equals to this. And you can see these two are the same thing, even though it's, because these are integers, right? They commute, right? So this is the same thing, okay? So therefore, Amir and Bob have magically, well, through the power of cyclic groups and in this case the power of mathematics, they manage to share the secret key together, a common key, without being in communication with in cross in close contact with each other. They can just do this. If one of them changes the key, their personal key, all they have to do is to repeat the same step again in order to generate another secret key. That's it. And anyone else who wants to communicate with them will use the same scheme. Okay, so now this is the best time, is the right time to go back to the chat to see if there is anything confusing here. Let me go back. First of all, am I on? It's like I'm blah, blah, blah. I was still on, right? Yeah, it's like magic. So, so is anyone confused about the protocol? Was I confused? It's more confusing probably me trying to explain it than actually following the diagram yourself. I'm happy to go through it again if there is anyone. Is there anyone? Is there anyone who is confused about this protocol? Okay, for me, okay. So Barry is okay. Anyone else? Don't feel, this is, this is not it's not, don't feel shy. You can ask. Maybe I wasn't clear on something. But I think even the diagram, as you will have access to it, will be self-explanatory, really. And I will correct this. There's a typo here. This key, this meant to be n-2 for technical reasons. This is in practice what cryptographers do.
I found the diagram helpful, but okay. I have one little question.
Yeah.
What if Bob and Amir's key collide. Since they're both picking them independently, they could pick the same.
Yeah, that's an interesting question. What do you think? The thing, I'll leave that as a food for thought for you to go through to see if you can get it by the study, by the study session. It's a very interesting question because yeah, it's true. They can obviously the two keys can collide. Yeah, and what will what will they do? You know, try to get there, and especially in the on the computational side of things here to see what if they will get to anything. But obviously, ideally, you want them to be as random as possible and distinct, right? It makes it. This also comes in with the if the two they collide, then it means life becomes a little bit easier for a Diffie-Hellman problem, right?
Yeah. But given that n is large, it is very unlikely to.
Yeah, but it's a good question. Actually, it's a good question, and I encourage you to go and think about it and bring it back. I'll probably join your the next study group actually to go and listen to your discussions and maybe add some points there.
A and B will be the same in this case, so you will be able to tell that they collided.
Right, you'll be able to tell. Both sides will be able to tell there was a collision, but I'm still not sure if there's any implication for Eve. Of course, Eve would not know anything, but I still think it's a bit of a puzzle. But thank you.
Well, Eve would also know that they collided, so it's the same key. So now, I don't know, that probably makes it a little bit easier to break it, but it's a small problem.
Valid point, yeah. Carry on, go on.
Yeah, but I guess since you can detect the scenario, you can repeat until you get different keys.
Okay, fair enough. You can tell if the scenario has happened, yes.
Mm-hmm.
In fact, Bob would know right away.
Yep.
Okay, so interesting conversation, guys. This is exactly one of the reasons I think you should just move. Let's George. I recommend you to go think about it and formulate something. Maybe in the study session you can bring it back to the thing. I will join your next study session. I will try my best to join it.
I'll regard it as an additional puzzle.
Yeah, and I will correct this. This is end to the thing. Okay, so now let's see a toy example. Okay, so I hope I didn't make this is a thing. If it's a good thing if I make any mistake here. Can you see? Is the diagram clear enough?
Yes, I can see it.
Yeah. Okay. So here's a toy example. Well, that's a little bit the thing. So we picked the cyclic group. There's star missing here, so the typo, the multiplicative group. So this is not. It's a F29 star. I mean, you know what I mean. So I will correct the typo again. And 2 is a generator for this group. That's what I claim anyway. You can double check me on that. Okay. So let's see. This is a concrete example. This is the thing for those of you who are confused with the abstract, with the protocol defined on the abstract. You can go through this example. You should be able to see it. Okay. So Amir picks his, let's say his KA, his private key, to be 5. Okay. 5 is in this range, right? Is in the range of 29 minus 2, right? That's what the protocol we were saying. You know, the best practice, the order. I mean the. Actually, there might be some typo somewhere in the thing. I will let you actually try to find it. Yeah, but anyway, it doesn't matter. Let's say that Amir Amir picked the key, his private key, to be 5, and the generator we know is 2. Okay, so Amir takes 2 to the 5, which should be 3. I hope you can correct me on this. Okay, so he sends A equals 3, right? Bob receives A equals 3, and then let's say that Bob's instead of picking 5 like Amir did, like the scenario that George was thinking about. There's something. There's a bit thing on the order here, because this is prime. This is a prime number. I hope you picked it up. But it doesn't matter. Still, the thing can still function in a way, because we are worried about KB here. It's within the range anyway. So KB. So Bob picks KB equals 12. Okay. So Amir sends A equals 3. Bob picks the key, and then he raises 3 to the 12, which in mod 29 should be 16, I hope. Okay. And then, so that's Bob's secret key. Okay, 16 is Bob's secret key. Okay, because he picked number 12, and because he receives 3 from Amir, all he did was to raise 3 to the 12. Okay, in mod 29. Okay, and then Bob will help Amir get his private key. So Bob will Bob will do. Bob has the generator, right? Bob will take the generator 2 to the power of 12, which should be 7. I hope. And then Bob will send 7, B equals 7, to Amir. And then magically, voila, Amir will take 7 to the power of 5, which should generate 16. So both of them have key equals 16. So there you go. There's some ambiguity somewhere on the thing to do with the. I hope you can pick it on the thing, on this, the fact that this is a prime. I'm pretty sure you will be able to pick it. I will correct the slide. Okay. Could you see what could be a problem there? Or is it an invention? Because remember, I said the N is the order of the thing, of the group.
Oh, I see. So you meant to say that this is Z29 and not order 29. Okay.
Yeah.
Yeah. Okay.
Yeah. So you see Dimitri already, but it would be good for the others to see the thing, the mistake here on the thing, on the not on the abstract, on the thing, but on the concrete use case here. Okay. So now, I hope it's not confusing. Even with that mistake, it's okay. It's fine. What matters is the parameters that both of them picked, which are correct, which are fine, admissible. And yeah, I hope you go through this and you will be able to understand. I encourage you, actually, two of you, like to do like some sort of a game between two of you, in the study session or separate, whichever way, for you to play this game to see, you pick a cyclic group, you pick a generator, and then you play this game. You pick a random thing, don't tell each other, and then see whether you will get to the same conclusion. You will see. That's actually the best way of practicing and seeing that the protocol works.
So I have a question. I tried to find generators for very large groups. And I think that finding a generator, my suspicion is that it's a very hard problem. It seems to me to be equivalent to the discrete logarithm problem. So I wonder how they come up with these generators.
There are some I can share you some resources on generating the thing, coming up with the generators. But it's a hard problem. Whether it's equivalent to DLP, it's saying this is something that I'm not sure. But it's not. It's non-trivial. It's not easy. Yeah. It's not straightforward. Let's say.
Yep.
I mean, finding the cyclic group is easy, right? Because you know, that's why one of the reasons prime numbers are very useful, right? You just take the multiplicative, just take the prime field FP, and then the multiplicative group. That's it, But then finding a suitable generator, identifying the generator themselves, and and then let alone picking one. That's one of the things. This will take us more into realms of cryptography, which is a little bit out of the scope of this in a sense. But it's a very, very, very interesting question. And now I'll stop sharing this because I want to share another thing. I think we will. I promise we will finish in a minute. Before that, let me go back again to asking the question. How did you find this thing of the Diffie-Hellman thing? How easy it is, this at least to understand the protocol now that you understood cyclic groups?
I think it's very elegant.
Anyone else want to say something? There's something else I forgot to add. I'm basically adding an extra slide. Please bear with me. If you have to go, that's fine, because I will add this. But I just wanted to add something extra. Just one slide. I forgot to add it on the other one because obviously I have different slides. Anyone else? Dimitri, you want to comment? I know, Dimitri, I think you commented at some point some that you did the Elgamal.
Yeah, I was working on implementing RSA and Elgamal. And
okay.
I have a toy project just to play with this. Yeah. So
well, maybe that could be an interesting thing to. Yeah, go ahead. Sorry.
Yeah, I use this. I found this Miller-Robin primality test to generate large primes, and yeah, I can share this actually.
Okay.
If people are interested, have it on a GitHub repository.
Yeah, because they would see another application of cyclic groups on the thing, a concrete useful application of them.
Yeah, and I will add the DHP algorithm now that you that I know that you showed it to us. It should be pretty straightforward.
Even if it's not, even if it's not on the thing, you could have another session. We could organize another session for you to just go through it, through the Elgamal and the thing. It doesn't have to be during the study. If it's the time is limited for that, I'm happy to schedule another session that you choose convenient for you, and we do that.
I could do that, I think.
Okay. I found what I wanted to add. Just bear with me, guys. I will, in the next 10 minutes or less, we should be able to finish. It's just I forgot to add this.
Thank you for sharing, Dimitri.
Yeah, no problem.
There is actually, I will share this now that we are talking about cryptography. I think there is a talk by Elgamal himself in one of the meetups I saw. It's with Jack Hidari, the guy from Sandbox AQ. There's a meetup somewhere. I will find the link. Elgamal is actually going to be there about talking about post-quantum cryptography, something like that. I haven't registered it. I just saw it on my feed and I bookmarked it. I'll try to find it and then send it because it's relevant to this. You'll see the man himself. Hey, bear with me. I'm gonna Anyone else had any difficulties to understand the protocol? Please feel free to comment on the thing. I can go back through it and As you can see, all you needed to know is the bare minimum about the stuff that you cover, right? What a generator is, what a cyclic group is, what a generator, and the basic property of exponentiation. That's it, group exponentiation.
Yeah, I know. I also found it amazing. I mean, how few concepts you need to get to these relatively advanced crypto systems.
Yeah. Okay, so I think I should be able to share now before we wrap up. Bear with me. Okay, no. Okay, you should be able to see this. The Diffie-Hellman problem.
Yes, I
now
see
you
it.
understand why the Diffie. Now that we went through the protocol, you understand now the connection between this. You understand how why this is important to the protocol, right? Because if you can guess this, then you essentially you got hold of the thing, you broke the security protocol of it, right? So and the other thing I wanted to share is the final thing on this other slide. Is that for most practical applications of the Diffie-Hellman key exchange, these are the multiplicative groups. Again, there is a star missing here. So, FP star, where P is a very large prime number. Let's say, as large as what you would pick for the RSA, prime number, and P is also safe prime number. This is another technical thing that we will just ignore. Okay, you can go through these on the thing on the pages, on the standards. Is it NIST or these other resources about this, where they can, in terms of implementing the best practices for implementing that, you will have all that this sort of information. So FP star is one of the most used. This is what most people are familiar with. Now, the more exotic ones, not is this thing here. This is something that we didn't touch. At some point when we do more, cryptography, or touch about field Galois theory and field extension and this type of stuff, this multiplicative group is also very used. This is a little bit more advanced. Is multiplicative of Galois field extension of this thing. This is the field of polynomials over the Galois field prime field 2. It doesn't matter anyway. Yeah, this is a little bit complicated. There's some other stuff that another thing is the elliptic curve, the multiplicative group given by the elliptic curve. Okay, that's also some, but that's very, very like frontier, like exotic stuff. In practice, in most protocols that you see, stable ones that have been been used, is this. This is FP, F star P is the thing, the common. Okay. And the final thing I want to comment is that the Diffie-Hellman key exchange protocol is essentially ubiquitous. It's used in very popular, important protocols, including the stuff for those of you who are developers. You use SSH all the time. The TLS, IPsec. All these guys underpinning, and they all have Diffie-Hellman underpinning them. Okay, so it's a very, very important protocol, and you just understood how the mathematical basis of it. So congratulations and well done for having the patience to going through all this, and I hope it was worth it. And this will be it in terms of cyclic groups. And I hope some of you will be curious enough to go into cryptography, because you definitely have the basis now to go through some of the cryptographic protocols that we mentioned before. So that's it from me. So Anyone have any final question or any final comment that you want to make?
Thank you very much. That was extremely interesting.
Thank you. Yeah, I think the trouble you took with the diagrams was worth the time.
Yep.
Thank you. I thought so. I didn't want to. I was initially my plan. After 1 hour, I saw this thing was very wordy, and it would be like I myself, I struggle with words, especially when trying to formalize something. It's a little bit when you add too many words. It's like so. I was like, diagrams is probably easier to go through because you can see the flow, and it's easier for people to think.
Yeah, the flow and the direction where data is flowing from whom to whom.
Yeah. So I hope you in the study sessions, you come back with some of these interesting questions that you were talking about, you were bringing about, these scenarios. What if they, they happen to pick the same random thing? What will happen? You can actually try to, simulate that scenario and see what you come up with. And I really recommend you, now that you know the protocol, to pick someone else, between you or even 3 people to see, to play around, Diffie-Hellman to see what it does.
And it is very easy to play with by hand, even in your head, for small n to see the patterns.
Yeah, especially with the thing, because I definitely recommend you, definitely George, as George was saying, you don't need to pick a big multiplicative group. I mean, big group with large order. Just pick small one and just play with it. It helps you gain the intuition of how these things work, and you can actually prove it. See the concrete. If you were not convinced about the actual abstract proof of it, you can just try several concrete examples. You will see that you will always get to the same shared keys. Okay, so I know it's been like it seems like we are like running over 1 hour. Anyone wants to make any comment on these things before we go? Any final question?
I don't see anything more in the chat.
And George, I assume you're still going ahead with next week's study session.
Yes, I think that's been going very well. More people are
Okay.
joining, and the more people that join, the more fresh ideas and approaches.
Okay. Okay, good. So yeah, in that case, thank you everyone. And yeah, I'm actually trying because we've been embedded in cyclic groups. I'm trying to see what next, what makes more sense to make the transition to another topic. Yeah, so yeah, I have to think about it. Yeah, but I hope you enjoyed this cyclic groups. At least it gives you a context of how abstract group theory, even at this point, at this level, I won't say elementary level, but at this not too deep level, has something useful, something practical that you can go and build something with it and learn something. Especially I encourage you, those of you who didn't look at cryptography. This is cyclic groups could be your entry to cryptography. Because they're so simple. The notions that you need to learn, the concept that you need is bare minimum in order to understand. So yeah. So thank you so much, and yeah, if there is nothing else, and I wish you all a happy weekend, and see you next time.
Bye.
Thank you, and bye.
Okay, bye.